Hello, everybody, and welcome back to the Space Jams podcast. I'm your host, Jim Murphy, and today we're going to be taking a look at an interview I did a few weeks ago with someone very special from the National Air and Space Museum, David DeVorkin, PhD. David is a senior curator emeritus in the history of astronomy and the space sciences at the Smithsonian. He has a focus on modern astrophysics and the space sciences during the 20th century. He's written over 20 books. I would check them out. They're fantastic. And today we're going to focus on women in astronomy and in space in the 20th century. Tune in, listen up. It's a great interview. He gives a lot of great information. Here we go.
Oh, it was a great project. It started off with I knew that the American Astronomical Society was meeting in Long Beach, California, and my hometown is Los Angeles, Santa Monica, stuff like that. And I said, why don't we get together? The people I grew up with, are all getting kind of senior, and we all have experiences of what astronomy was like to the public in Los Angeles in the 40s and the 50s. That's 1940s and 1950s, 60s through the 80s and everything. There are some very interesting things about how astronomy was done in Los Angeles by the public as well as by professionals. So there's been plenty of histories of the professional astronomy there. But I said, why don't we get some people together who've been looking at the public side of things, the amateur groups, the groups that were open for the public, and then the amateurs who really made a life of bringing astronomy to the public. So we got together, and I contacted the director of the Griffith Observatory, Ed Krupp, and a few other buddies I knew, and we got together, formed a proposal. The American Astronomical Society accepted it for a full session, and pretty well highlighted session that got good attendance, and we had a great time. So that was it. And after it, we decided, hey, this might be something that really would make a great book. And some of the people I brought in were not authors. They were enthusiasts. And so we all had a good time putting them together. But there are some really good historians as well who did some excellent work. And so we have a range of personal statements as well as academic statements. And the book that came out, if I can show it to you and advertise it, it's not being distributed yet. As soon as the Griffith Observatory reopens and the Department of Parks and Recreation that published it gets its act together, we hope that it will be available, and it certainly will be when the Griffith Observatory opens to the public. Now, if you look at this cover, how many people have seen like a car from the 1930s with a telescope on top of it? This guy Studi, that's his name there. And I thought the car was named Studi. I thought it was a Studebaker, but it isn't. But his name was Studi. And he built this thing, and he would take it around the LA and set it up on street corners and just invite whoever's around to come and look. And he was just one of many people who just did this. I mean, you had real clear skies in Southern California, and the sky was a big part of your life. So we put together these articles, had a great time. Moving along those lines, what I want to show you today is a progression of the work of a set of women that we chose to be representative of women who worked in astronomy and were astronomers from the late 18th century through to today. And the whole point of it is to show their changing roles, how they changed from being, let's say, the sister to being a hourly paid worker to a sort of like a junior associate to a full associate, and then to be independent and fully vested in astronomy.
Well, there you go.
Yeah, and it's in the gallery. This is called Explore the Universe, and hopefully, when I guess we open pretty soon, I hope that gallery should be visible for at least, I think, another year. We're undergoing a complete renovation of the museum, and every gallery will be changed. The one that I'm talking about will be one of the last ones to be changed. So it'll be visible for at least another year, I believe. We're looking at 1, 2, 3, 4, 5 women. And there you go. There you go. That's right. You can scroll up and down. And these women span astronomy since the late 18th century through to today. And they are, you might say, representative, but also stars of the role of women in astronomy over this time, and they changed. In the top left corner is Caroline Herschel. She was a singer by training in a family of musicians. Her brother William was also a singer. No, sorry, he was more of a conductor and orchestra and stuff like that. And he left the family in Hanover, Germany, and he moved to England. And he was an amateur astronomer at the time. Now, he wasn't a typical type guy. He wasn't interested in the astronomy that everybody was doing. He was kind of a very impulsive guy who loved to build things. And one thing he loved to build was big telescopes. And he ended up discovering, he was the first person in the history of the world, you might say, to discover a planet, a new planet. We always knew about Mercury, Venus, Mars, Jupiter, and Saturn, before we even knew that the Earth was a planet. Those were the planets, the moon, the sun, that sort of thing. But in the era of telescopic astronomy, the first new planet that was discovered with a telescope was done by Herschel. And he, of course, wanted to call it after the King of England at that time. But it ended up being called Uranus. But the King of England was so impressed that he gave William a lifetime pension and made him the king's astronomer. Well, that gave Herschel quite a bit of you might say, resources. And he invited his sister to be with him in England. At the time, his sister was the youngest in the family, and she when she was in Hanover, she wasn't treated very well. She was mainly and that's Carolyn right there. She was mainly a service person in the family. Anyway, though, she was a singer, and Herschel brought her to England so that she could sing in the choir that he was setting up in a church in Bath. But anyway, he was doing his astronomy, and he was jumping back and forth and jumping back and forth. But Carolyn was kind of a systematic person. She was very, very organized, and she looked at William, saying, you're building these big telescopes, and what you should do is be more systematic. Yeah, that's the telescope now that William used to discover Uranus, and he built it himself. And it would be considered a moderate telescope by today's standards. And there was nothing particular about its design other than he made it quite mobile, and he could turn it around quite a bit, as you can see. He'd look through the eyepiece in the upper left darker portion of the upper tube. There would be like a 6 or 7 inch mirror at the bottom of the tube, and the light would come in the top, go to the bottom, focus back onto the top where he stuck his eye. And that was a really cool thing at the time, when at first he thought he discovered a comet, and everybody was looking for comets so they could get their names after them and stuff. That was the big thing, discovering comets. But then he noted how it moved, and other people examined it more precisely, and they said, it's not moving like a comet, it's a planet. And that really did it. Well, anyway, he started building much, much bigger telescopes. And he was a real gadfly, just trying all sorts of stuff. But when Carolyn got on the scene, you can go to the next slide. When Carolyn got on the scene, she systematized him. There's a nice picture of his telescope in front of his house, and by this time they'd moved closer to London, and you see Carolyn there in profile because there are no graphics of her when she was young. There are graphics of her later in her life. But the idea at first was just to build a bigger telescope to try to see to the end of the universe. And he and Carolyn devised this technique, and he came up with making some assumptions. He said, okay, I want to build a telescope big enough to see to the end of the universe, all right? Because he thought, the universe is finite. And his next assumption was all stars are the same brightness, and they're kind of equally spaced. Now you put those things together, and the number of stars then that you see through your telescope in any one particular place in one direction is an indication of the distance to the end of the universe. And so Carolyn and he was saying, well, let's, that's a great idea, but let's do this systematically. Let's go, like night after night, looking at these star fields covering the entire sky, and let's keep track of it. And she would sit in the upper window there of the house, and he would be on the telescope there, and they would simply map the heavens, but she would record it. And it was her work that really created the systematic nature of this huge project that went from the 1780s through the 1790s. And by about 1800, they had a map, a very highly detailed map of the universe, and it started asking some questions about it. Now, part of this is, since this is a tour of our gallery, I want to show you how we brought this telescope to the museum. This is another graphic of it. And I should say that he modified his telescope in order to allow it to see to the end of the universe. He got rid of the small secondary mirror in the telescope, and he just had a single reflection of the big mirror. These mirrors he made, they're speculum metal mirrors. They only had a reflectivity efficiency of about 60–70% at best. So if you reflect off of two mirrors, you're only going to get about 30–40% efficiency. And he wanted to see as far as possible. So he made a telescope big enough so that, as you can see in the upper right here, there's a little figurine that the craftsman is holding. He would look through the telescope from the very top without using that secondary reflection. And you can see in the diagram there on the left, that's how he would do it. And then he would do this in complete darkness. Carolyn would record his observations in a book and then tell him what to do next. And so they worked on this for years and years and years and years. Yeah, I should say, in the gallery, we have this telescope, and it's the real one that he used. It's called the 20-foot reflector. It was made over a period of years. It was remade in several times, but the tube is and the mirror. The tube was remade a number of times, and you can see William there at the top of it, and Caroline you can see in that little window there. The tube of the telescope is that big thick thing that's at diagonal going up to the left. The mirror he made, and it wasn't the first mirror, it was a later mirror that he made with the sun, you can see in a case Yeah, exactly right. And that was about 18 inches in diameter, had a long focal length. That was a big telescope at that time. Now, uh, what we have that's original here is the mirror and that tube. The tube, of course, had been refurbished several times. Our technicians, our artists, our people, specialists building the exhibits did a fantastic job of recreating the mounting around it. And even to the point, if you can see that iron fence there, they used iron filigree that was appropriate for the time, the Georgian period. So Herschel would make his measurements, and then a model. And of course, there's Caroline recording. Now we had an artist, and we had no pictures of Caroline as a young woman. But the artist put in just a captivating picture. Turns out to be the artist's wife. So he got his wife in there. Go back to the other one just for a second. On the left-hand side, just to the left of Herschel, just above it, you can see a artist rendering of the map that he made, that they made. It shows the distribution of stars, and then it shows these fuzzy objects outside of the map. And this is what Herschel found, was that all of the stars that he counted seemed to lie in a band across the sky, most of them. We call it the Milky Way. But then when he also, as Carolyn pointed out, examined the fuzzy objects, what were called nebulae, he found that they avoided the Milky Way and they were every place else in the universe. And he started asking, they both started asking, are these other universes, or are these solar systems in formation, which was a theory at the time? What were they? Next slide. This was Herschel's, next after that. Yeah, this was Herschel's schematic model. The stars were primarily in that rectangular block with that little offshoot on the top of it, which pretty much represents the distribution of stars in the Milky Way. But the nebulae were everywhere in that sort of like in that circle around it, like that. This was sort of a distorted schematic. And so he asked, really, do other universes exist? And that was the question he started posing around 1800, 1810. And that was not answered until the 20th century. And it took quite a bit of work by many, many people. But then I wanted to turn to the next woman that we want to cover, who is Henrietta Swan Leavitt.
Before we move on real quick, now did Herschel and both the Herschels, I guess, they were contemplating the idea. They were looking at the Milky Way. Did they ever kind of understand what they were looking at? Did they ever understand that they were within the Milky Way?
Yes. Yes, they thought they were at the center of the Milky Way. And because all the stars around in the band, where there were pretty much equal numbers of stars everywhere. Go back to the previous slide. Let's see. I think it's marked. Yeah, you can see the mark there. In the rectangle, there's a large spot. Yeah, that's it. That's where he thought the sun was, and the Milky Way itself. It was around it, and then there were these other things around outside the Milky Way, and he was thinking, maybe could these be solar systems in formation, which was a strong theory at the time, or are they other universes? And he posed the question, but then he didn't do too much with it at that point. I mean, he was toward the end of his life. His son, John Herschel, continued the work, took that telescope to the southern hemisphere, to South Africa, and continued the mapping so they could map the entire sky. And so this question continued for many, many years. Now, the question is, how was it answered? Well, the key is, how far away are these things? That's the big key. If they're relatively close, then they could be solar systems in formation. out of nebulae. There was a theory at the time by Simon Pierre de Laplace saying that the solar systems, or the sun and the planets, formed out of a nebulae, and the nebulae collapsed into a star and planets going around it. And that was pretty popular. There was no proof, but that was a pretty popular idea. But the question is, how far were these things away? That was the big question. So if we move on now to Henrietta, she started the ball rolling. By the late 19th century, there were various ways of determining distances to stars and that sort of thing. There was a technique called parallaxes. And I don't know, you know that technique, that if you hold your thumb out and look at a distant object with your right eye and then your left eye, your thumb sort of shifts back and forth.
Yeah.
Okay, well, that's a measure of the relative distance between the distant object and your thumb. That's called triangulation. And some of the closest stars were measured by triangulation. But then trying to see deeper and deeper into space, there were other techniques that were being developed. But meanwhile, Henrietta Swan-Leavitt was a worker at Harvard. She was hired by, next slide, Edward Charles Pickering, because Pickering and his observatory, they were collecting so many photographs of the sky, because now we're talking about telescopes and photography. And with photography, you can just collect millions of images. And who's going to, analyze them? Who's going to measure them? Their brightnesses, their positions, and everything like that. Well, what do you need is low-cost labor. And next slide. And what you get is women. And here is unfortunately, slightly fuzzy slide of the women in what was called nicely Pickering's harem. He hired quite a few women to do this kind of work. You see that they're all studying the plates. And unfortunately, the slide is a little too fuzzy, but on the wall behind it, you see that little chart there? Yeah, the rectangular chart. You can sort of see some wavy lines on it. And what they would do there was they would follow the brightnesses of stars. They found that stars varied in brightness. And why they varied was unknown. At first, they thought, well, the stars must be eclipsing, it must be double stars, and one goes in front of the other. And when they're in front, then the light of the back star you can't see, and so the light goes down. Well, that model worked. It was popular, but it didn't work that well. But meanwhile, they were cataloging all these things. And one of the jobs that was given to Henrietta was to examine stars in a very, very particular part of the sky. Now, Harvard had observatories all over the world. And one of them in what was called at that time the Boyden Station in Peru was paying attention to two very interesting objects in the southern hemisphere that we can't see here. They're called the Magellanic Clouds, or the Clouds of Magellan. And Magellan was the first one to record them and see them and bring the record back to the European world. Of course, the clouds had been known by indigenous peoples for millennia. But we call it Magellanic because he was the first one of European ancestry who saw them and wrote about them. Okay, well, the problem was, hey, let's try to find variable stars in these clouds, because it'd be interesting. What we know about all of those stars is that they're all at the same distance from us. So whatever they're doing, let's see if we can see, if they're changing in light brightness, if it's correlated with anything else about them that could give us some kind of tool for measuring things like distance. So let's see, I think the next slide. Okay, yeah, there's Henrietta. And she was given a job to measure these stars in the Magellanic Cloud. And I'm sorry, we don't have a picture of it. but she was given this assignment to record their brightnesses and their variations. And if you go up one slide, okay, here we go. What she found, think of these two stars. There's dim stars and bright stars, okay? And then there are periods of variation, short variation and long. And what she found was that there was a correlation between the brightness of a star and how fast it changed in brightness. The relatively dim stars, they would change in brightness 1 or 2 days, 3 days. But the brighter big stars, they would took much longer to change in brightness. So what does that give you? That gives you a relationship, a correlation between the period of brightness variation and how bright the star was intrinsically. And that is a really key tool. Now, she realized that, wow, if I could simply find the distance to any one of these kinds of stars close by, like from parallaxes, then I could calibrate this whole thing and get use this as a distance indicator. It's called the period luminosity relationship. So basically, in the gallery, what we have is a panel on her and how she created a cosmic yardstick. These variable stars were called Cepheid variables, and that's because the prototype type of variation, and it was slightly asymmetrical, so it was a characteristic curve. No matter how bright or dim the star was, it always had a very similar curve, and it would change color as it changed brightness. And so she looked at these classes and established this period luminosity relationship, and then immediately people, astronomers, were able to jump on it and use it to determine distances to things. Now, she wanted to do it herself, but as the story goes, here she is, a woman working on an hourly wage, doing what she was told to do, and she wasn't really allowed to exploit it herself. But within a few years, others did. If we go to the next slide, the Harvard astronomer at the time, he wasn't at Harvard yet, sorry, he was at Mount Wilson. He used the period luminosity relationship to determine the distances to what are called globular clusters. Those are spherical clusters of tens of thousands of stars, and there's variables in them. And so what he found was that the globular clusters seem to be clustered around the center of the Milky Way. This is an exterior view, of course. We're taking a modern view. And from where the sun was thought to be, he decided that the sun wasn't at the center of the Milky Way, because he looked at the distribution of globulars and found that they centered not on the sun, but they centered on the brightest portion of the Milky Way. And so he suggested by 1918 that we're not at the center of the Milky Way, we're toward the edge, and this is called the galactocentric revolution. So that was the first revolution that was brought about by her stars, but it didn't end there. Move to the next slide. Just a few years later, Edwin Hubble found Cepheid variables with their characteristics in the Andromeda Nebula, which was one of Herschel's nebulae that he said, well, where are these things? And with the brightness of that star, and you can't even see it. You notice at first he put an N there, and then he crossed it out, and then he said "ver" with an exclamation point, because he knew he had discovered something big, big news. And that tiny, tiny star between those two bars that we can't even see here was a Cepheid variable, because he kept on following its curve, and it was so faint that this nebula had to be much farther away than the size of our Milky Way. And what does that mean? It's an island universe. And so Edwin Hubble discovered galaxies based upon Henrietta's work. What else was learned from the Harvard materials? Well, one of the things that Pickering had done was to institute not only pictures of the sky that are straight like our eyes would see them, but images of the stars broken up into their spectrum. And you produce a spectrum by using a prism, send white light through a prism, and you get color. We call it a rainbow. Rainbows are produced by thousands and thousands of tiny little, billions of raindrops acting as tiny prisms. And if you put a prism in front of a telescope, you can produce that rainbow. Now, in a black and white picture of a rainbow, everything looks black and white. But that is scientifically much more useful because you can gauge the changing nature of the star's spectrum. And what they did at Harvard, Annie Cannon in the upper left, who worked alongside of Henrietta Swan Leavitt at the same time for the same 25 cents an hour, or maybe it was 5 cents an hour for all I know. That's one little thing. People say they were mistreated because they were paid so little. Well, I did a little work and I found out that that's what a school teacher was paid at that time. So it was typical for a low-paid person. But anyway, what Annie Cannon had found was that stars of different colors had different kind of spectral signatures. Like, think of those as fingerprints of stars. And they seem to be correlated with something like temperature, but also they might have been correlated with how much material there is in a star, how much hydrogen, how much iron, how much oxygen, that sort of thing, they figured. And no one was able to separate out the effect of the brightness of these dark lines, which are the absorption lines produced by different elements in the atmospheres of stars. The Harvard system, which Annie Cannon created, was finally accepted and verified by the woman below, Phoebe Waterman Haas, who did her PhD thesis at Lick Observatory using that telescope on the right. It's in the gallery, the spectroscopic part, which is inside that rectangle. The telescope, of course, is 60-something feet long, and that's just a picture of it. That's the one I used at Lick in the 60s. But anyway, Phoebe used it in 1910, 1911, and 1912, and she was one of the first women to get a PhD in astronomy. And what she did with it was to verify the Harvard system. So now that they knew that this Harvard system of classification was what was real, what do you do with it? And the big question for them was to be able to separate out what caused those different lines to be dark and to be less dark. What governed the strength of the lines? Could it be composition or could it be temperature? And the person who figured that out, we move one slide down, was another Harvard woman, Cecilia Payne-Gaposchkin, in the 1920s. Now, Cecilia came to Harvard not as a paid hourly worker. She came as a student. She was one of the first not the first, but one of the first women to get a PhD in astronomy. But it wasn't at Harvard, but it wasn't from Harvard because it had to be Radcliffe. But that's just the nature of the beast. But what she did was she was able to separate out the effect of temperature from the effect of abundance. If you, scroll, okay. Here is a graph that shows the visibility of different elements. The H is hydrogen, the Ca2, that's calcium, TiO is titanium oxide, the Fe is iron of different ionization levels. The He is helium, the Mg is 2. Now, as a function of spectral type, what's the strength of those lines? And you can see the spectral types, the Harvard spectral types here on the bottom go from what is called OBAFGKM. That's the Harvard system. OBA, fine girl, kiss me. That's how I learned it until somebody slapped me. But anyway, you can also see that those were the O stars were the hottest, and the M stars, the red stars, were the coolest. But what she found, looking at all these elements, you can see that no matter what the temperature range, hydrogen was always present, no matter what. Calcium was also present, but other elements were only present in very, very small ranges. And what she did was she interpreted this as being an abundance feature. The more abundant an element, the more probable it will be visible. And the one that is most visible was hydrogen. And from that, in her PhD thesis, which had been declared later on as probably the most brilliant PhD thesis ever written at the time, she said the sun is made out of hydrogen.
Yeah.
And up to that point, most people said, hey, what's the sun made out of? That's the same stuff as the earth is made out of, right? Okay, you got your dirt, you got your iron, you got everything, just heat it up and that'll be the sun. Well, what she showed was that's not true. Hydrogen is the primary component. Of course, iron is important and calcium is important and everything, but by far, hydrogen dominates. And so she revolutionized, of course, she knew that this was radical, okay? And she was very smart, politically, very smart. And in her thesis, she said, well, this is my result. But Henry Norris Russell, who was the big name in the field, said, nah, it certainly can't be correct. But I'm going to put it in my thesis anyway. Now, there are people who've said Russell didn't believe her because she was a woman. Well, that's not true. There were 3 other people in the mid-20s who were coming up with the same thing. And he didn't believe them either. And they were all men. So it made no difference whether they're men or women.
Huh.
Finally, though, by 1929, the evidence got so overwhelming that Russell finally had to accept it. Yeah, the universe is made out of hydrogen and we're in trouble. Why were we being astronomers at the time, why did he resist it? There's nothing, what's the matter with hydrogen? Well, the way that different elements behave can tell you how a star behaves. If a gaseous element can absorb light very well and heat up, it can be buoyed or supported by a radiant light source. Stars are great globes of glowing gas. That's the way to describe them. But there's 2 forces acting on a star. It's the mass of the star compressing it, but then there's a nuclear force in the middle pushing it out. And if those 2 forces are in balance, like our sun is, thank God, okay, because we could not exist without our sun being in perfect balance, the star is stable. But if the forces are not in balance, they will pulsate. And that's what the Cepheid variables do. That's why they're varying in brightness. But what Cecilia showed was that this is the abundance ratios of elements in the sun are completely different than the Earth. And that created problems for people like Russell and others who had built theoretical models of stars that did not work if it was hydrogen, because hydrogen was not opaque enough. It didn't absorb enough energy. So this was a real crisis, but they finally had to accept it. And then that changed our view of how stars work in the 1930s, and eventually led us to our modern understanding. So Cecilia is sort of the second stage in the role of women in astronomy, because she came as a student and she continued at Harvard as a researcher. she still had to, she was encouraged, you might say, by the directors to do certain jobs, but everybody was under the thumb of the director. Nobody really had a free line. So she was pretty much operating as an astronomer. So that's sort of the second stage. Okay, let's move on. Go back through these. Go beyond that to Hubble. Okay. Okay. The next person we discuss and present in the gallery is Vera Rubin. Now, she represents more independence than Cecilia did. Cecilia was still very, limited. She was a woman. She was probably the best astronomer around. Even Russell, later on in the 30s, said, when he was looking toward retirement, he was saying, well, the person who could replace me, alas, unfortunately, she's a woman. Now, how he felt about it, because he said, alas, it's too bad, I'm not particularly clear on, but it was pretty sure that Princeton, where he was a professor, would not allow women, not only as students, but as professors. So he knew it was not possible. He was a very pragmatic guy, and he wasn't a fighter. But now, what about the next step in women's independence? Vera Rubin is a really, really good example of that. This is also a scene from the gallery, and we present Vera Rubin and the instrument she used to determine that most of the universe that's out there we don't see. It's dark. Now, by dark, it simply means that we can't see it by any known means, but we can feel it. We can't see it, but we can feel it. In the gallery, we come up to this point after going through all parts of the spectrum to see how stars shine and how nebulae shine and everything like that, and then ask the question, is that all there is? And the answer is that Vera showed us, finally, even though it was suspected for years, for decades, people were saying there must be more mass out there because the way things move in the universe, they're moving too fast for there to be any kind of stability. The universe would just evaporate. Why do these things, why do these clusters of stars still exist or galaxies still exist? They would evaporate because they're moving so fast. Well, what keeps them together? There must be hidden mass, missing material, missing mass. Vera was the first one to be able to devise an observational program that created enough evidence that made everybody believe, yep, we got to deal with this dark matter. It went from being a hypothesis to a fact that we have to deal with. And so how did she do it? If we move next slide, here's the instrument she used. This was called a spectrograph, which is the same sort of thing that Annie Cannon used the data from. The light comes in the top, goes through a slit onto a lens that collimates it, makes it parallel, onto a grating, which is at the bottom. A grating is like a mirror with millions of very fine lines etched into it, so fine that it breaks up the light into a spectrum. And that grating produces a spectrum, just like a prism, that is then focused here and then is moved up here. But the key about this instrument was it had a very special electronic amplifier, that's right, that amplified that spectrum, that signal, 100 times to get on that tiny photographic plate. Now that made this an extremely powerful spectrograph. And Vera had access to it because it was built at the Carnegie Institution of Washington where she worked. And the guy who built it was looking around for interesting things to do with it. And Vera came up with this really interesting thing to do with it. Let's examine how the Andromeda galaxy rotates. Let's do that in a finer way than has ever been done before. Now, Andromeda is the same one that Hubble used and the same one we showed that Shapley used. It's the closest galaxy to us, so it's the best one to study. So move one slide farther down. Okay, Now, what everybody knew was that a galaxy seemed to rotate like in a swirl, like a whirlpool. You know, you look at a whirlpool and the center of the whirlpool is rotating faster than the outer edges of the arms, right? You know, look at a sink. Let water go down a sink, and the water swirls faster and faster as it goes down the spout, right? Well, the expected line for the rate of motion for the stars, yeah, the dotted line, that is what was expected she would find. But what she actually observed was a flat line. Yeah, go to the next slide, it's better. Here it is. Okay, there's Andromeda. And she was looking at the velocities as a function of distance from the center. And she expected that dotted line, but she observed that dark line. So instead of rotating like a whirlpool, it rotated like an LP record. Ever hear of an LP record? You know, a CD, a DVD, you know, rigid rotation,
Yeah.
you know, like a tire. Okay. You know, the outer part would be rotating slower than the inner part. Well, that's not what she saw. And she started with Andromeda. She went to other telescopes, taking her very powerful spectrograph, and looked at other galaxies, and they all behave this way. And it was such convincing evidence that people finally sat down and said, uh-oh, it's real, and we've got to deal with it. And the point is, we're still dealing with it. We don't know what it is. Nuclear, particle physicists, atomic physicists are looking for this hidden matter. One speculation is it's a weakly interacting massive particle. That's the characteristic. So naturally, they're WIMPs, weakly interacting massive particle. That's physicists. They have a great sense of humor. So this is where we live now, and Vera Rubin really contributed to the fact that we cannot ignore, we can't sweep it under the rug. And so it basically, she created a new universe.
Wow.
Yeah. So then the next example we have, Vera, of course, was pretty much an independent researcher, and she worked in a non-academic setting, because in her generation, it was more difficult for women to get competitive academic jobs. And so she worked at the Carnegie Institution of Washington, which was a fine place, but they were more liberal. Now, Margaret Keller was not only one of the first women to be trained at Princeton, which had been very chary on admitting women for quite some time, but she also got an academic job at Harvard. She joined a team of astronomers who were using this spectrograph, this little black thing at the bottom of this big telescope. And to explain what you're looking at there, the telescope itself is the white structure, the truss, okay? The mirror is down in the bottom, you can't see it. There's a secondary mirror at the top where that little red thing is. And then the light comes in the top at the upper right, goes down to the primary mirror, is reflected back in a cone, pretty much like those white lines there. And then from there, it is reflected back and concentrated onto this black object here, which is a spectrograph. It's a very, very, at the time, it was a very, very powerful spectrograph, because it allowed the astronomers to take literally thousands of spectra of galaxies and determine how fast they were moving away from us and from each other. And this allowed astronomers to start building a map of the universe, more detailed than before, where they could map the distances against their positions. Now, how would they do that? I haven't talked about it yet, But spectra, have you heard of the Doppler shift?
I have heard of the Doppler shift.
Yeah. Well, for everybody, it's like when an ambulance goes past you, the frequency of the siren, goes down. That's the Doppler shift. When it's higher coming toward you, then it's lower leaving. Well, stars do the same thing. They are, it's called red shifted if they're moving away from us, and blue shifted if they're moving toward us. And what Edwin Hubble, going all the way back to Hubble, found that there was a relationship for galaxies, and that the higher the redshift, the more distant the galaxy. And that's purely relativity. That's nothing. The galaxy doesn't know it. We don't feel it. But the farther we look in space at another galaxy where there may be people looking back at us, they don't feel it at all, but we're moving away from them. It's all, as they say, relative. So basically, this camera, this spectrograph, was able to record thousands of these radial velocities, they're called, these motions, and then compare them to their brightness, and they got their distances and their positions. And by the time Margaret came on the scene, there was enough data to start analyzing what the structure of the very large scale structure of the universe was like. And if you go back one slide to Margaret, there she is with a sort of a graphic image, and you're looking at a diagram there. This is only a sector of the sky, and each one of those white spots is a galaxy. And there, the Earth is at the very center there. Yeah, right. And what you're looking at is the distribution of galaxies in deep space. And are they even? No, it's really clumpy. And in fact, the one that she's looking at, it looks like some giant. You can see the body, you can see the two legs, a head, iron. Yeah, there you go. Yeah. And I don't know what they called him, but with more and more observations, the picture started getting more clear. And what you're looking at is a huge series of nested bubbles. Okay, we can move down a few. Yeah, to that one. And there's more data. By the way, there's Margaret in the middle, and the person who was running and doing the observations, he's on the right. That's John Hukra. And he had been at SAO using that instrument with others to collect all of that data. And then Margaret was the one who, with a graduate student, Valérie Laparent, started showing that galaxies cluster into huge bodies, and there are places where they're thick and places where they're thin, and they sort of represent bubbles. Go down to the next slide. And yeah, this is a larger view of it. And you can see there's areas of darkness, and then there's areas where all of these things are coming together. And she likened this to a surface of soap bubbles. And it showed that the universe on a very large scale is, you might say, uniform on the largest scale, but as you move up, it's non-uniform this way. And it looks like, at first they were saying, well, dark matter might be in the middle of those bubbles. No, that's not the case. What you're looking at are galaxies that are attracted by the dark matter, and the dark matter, that we still don't know what it is in this sort of a string fashion. There are strings of these things. And what causes that huge scalar string pattern, we don't know. Let's see, you can move down a little more. In the gallery, this is a video that shows a three-dimensional distribution of those stars. So we can just go past that. There's John with his one of his kids. There's Margaret. This is our presentation of them in the gallery. And again, another indication of that large scale imagery. Now, since the With this sort of data at hand, there were theories about the clustering and the overall structure of the universe that had already been developed, in fact, by Margaret's thesis advisor at Princeton, named James Peebles. But this pretty much confirmed the theory and helped to refine the theory. And in the next slide, you'll see how that theory was refined. This is the predicted distribution of cold dark matter in the universe that was developed partly out of the data that was in Margaret's analysis. And you can see that dark matter is not flowing. Where are we? Well, we're not in this particular image. We're here, but this is what the very deep universe looks like. And these little spots, they're not stars. Those are galaxies and clusters of galaxies. We're looking at a huge scale here, unimaginably huge scale. And that over time got more and more resolved. You can go to the next slide. And this is pretty much where we are sitting today, looking at the centers of not galaxies, but clusters of galaxies on a very, very large scale. This is the predicted distribution of galaxies and how they fit concentrations of dark matter.
So the lines that you're seeing, the clusters of galaxies, are not them being repelled from the dark matter. They're
they're being attracted.
They're along the lines of the dark matter. So where you see the clusters is where they believe the dark matter is.
Exactly right. If you go back, you'll see the same. Go back one slide.
Oh.
Okay, there's the structure of the dark matter. And if you go down back, you'll see the same structure with the known features.
Oh, wow. Yeah.
In the optical features, and it fits. So it's the galaxies and the clusters of galaxies are attracted by the dark matter. What caused that initial distribution? We still don't know. I mean, there are theorists who argue about it all the time, but that goes beyond what I can present here. So that's pretty much the story of the changing role of women as we presented in the gallery. And they are certainly not, everyone. You're looking now at a picture of Caroline in her late 90s, I think. She lived very long time. And we have Margaret, we have others, Beatrice Tinsley at the bottom there, very well known, and Margaret Burbage just to her right at the bottom. She worked with her husband and also alone on nucleosynthesis problems. So there's Sally Ride over there on the left. She was an astronomer. So this is just the smattering, and that's pretty much my my spiel.
It's fantastic. Yeah, well, with the whole stuff with the dark matter, we love a good mystery. So that'll be, something to look forward to. Somebody will figure it out.
Now there's a bigger mystery. It's called dark energy.
Oh, no.
We now realize that the universe is expanding, right? We knew that. But the rate of expansion is not constant with time. Something is pushing it out. And again, we don't know what it is, so we call it dark. But the amount of mass that is required to do the pushing that is measured now by astronomers is about 74% of the mass of the entire universe as we know it. Dark matter, that's dark energy. Dark matter is another 15, 20%. And then the last 4% is the matter that we see, the world we know. Oh. So our universe, we are in a universe of which only 4% we can actually see with our eyes or hear or feel or with any senses with our telescopes and stuff. So there's a heck of a lot to learn in astronomy.
Yeah,
it ain't over. So that's just the brief. That's my brief introduction.
Wonderful. Well, thank you so much for coming and telling us a little bit about women's role in astronomy. And I know I learned something. I very much enjoyed it. But we want to thank you for coming on.
Pleasure.
Yeah. Well, everybody, go check out some David DeVorkin's books. They're incredible. They've got a lot of them out there, and he has the new book coming out, Astronomy LA style, Public Astronomy LA style coming out. And he's got the cover right here. If you're listening to this, that's a good way to see it. But there's some great photos coming up, and that'll be the thumbnail right there.
It was like, what do kids growing up in LA in the 50s, how did they get interested in astronomy?
Exactly.
And this is the book.
Well, thank you so much for coming on, everybody. If you're watching this, you already know we're on YouTube. If you're listening to this, we're on YouTube. You can listen to us on Spotify, Apple Podcasts. Go check out some of the books. Ask us questions on Space Jam's Instagram. And, thanks for listening. Thanks for watching. And everybody remember to keep looking up.